Very good morning, students. Today we are going to see in second unit one more important chapter, that is your streamline, path line, streak line, velocity potential function and stream function under the kinematics of flow. As we already see what is kinematics of flow, we are going to study the flow parameters when the fluid is in movement. Okay, so that branch of science that deals with this behavior of the fluid in movement, that is said to be your kinematics. So let's go to this topic today, that is your streamline. So what is a streamline? It is a continuous line in a fluid, so which will be showing you the direction of the velocity of the fluid at each point along the line. See here, just imagine here we have a continuous flow of fluid here as it is shown. Okay, so if you take different type of particles, okay, that will be traveling along this streamline. So if you take any one particle and if you are drawing the tangent to this particles, okay, so at any point, okay, this tangent will give you the direction of velocity at that point. So this fluid particles lying on a streamline at an instant move along the streamline. Okay, so this will be moving along the streamline and they will be instantly moving along the streamline, this fluid particles. So what is the equation of the streamline? Suppose we consider this always that there will be three components exist in all the mutually all three directions. That is dx, dy and dz. So what is velocity? Normally what is velocity? Velocity is distance by time taken. So from this we will be able to know. So what is velocity? Velocity is distance by time taken. Here the distance is given in terms of s. Okay, so ds by dt. Now what is dt? dt is equal to ds by v. Just cross multiply this. So dt is equal to ds by v. Okay, so this is the case in case of the velocity. V is the velocity components. So here we have three perpendicular directions where the velocity components in three cases will be like u, v and w. Okay, so these are the velocity components of the velocity along the x, y and z axis. So what happens to this equation? Instead of v, we are writing this equation as dt is equal to dx by u, that is equal to dy by v, that is equal to ds z by w. That means we are showing the velocity in all the three directions. So what is the equation of the streamline now? So the equation of the streamline is dx by u is equal to dy by v is equal to dz by w. Okay, so this is the equation of the streamline. So when the fluid is in movement, the motion, there are many streamlines and these streamlines they will be indicating the flow pattern at the particular instant. Okay, when the fluid is in movement only we will be able to find out the streamlines, because we are able to draw the streamlines based upon the movement of the fluid particles. Okay, and the streamlines will indicate the flow pattern at a particular instant. For example, in a steady flow, the velocity at a point does not change in respect to magnitude and direction. Hence, there is no change in the direction of the velocity vector at a point in case of steady flow. In other words, the streamline is always fixed in position. From the name itself, you could be able to understand streamline means it will not change its path. Okay, it will not change its movement. It's always fixed in position. Or we can say that the streamline pattern remains constant when the flow is steady. It will be remains constant. But in case of an unsteady flow, so the direction of the velocity, what is the unsteady flow? It will be changes with respect to the time. Okay, the velocity or pressure or density, everything will be changes with respect to the time. That means the position of the streamline is not a constant. And the position of the streamline, it changes from instant to instant. Okay, so these are the main properties of your streamline. Next one is path line. From the name itself, you will be able to know what is a path. Okay, it is a suppose a fluid particle is moving, okay, in a single way or in a single path. Then if you are studying about that, okay, then that is said to be a path line. So path line is a path or a line that is described by the single fluid particle as it moves during a period of time. Okay, so the path line indicates the direction of velocity of the same fluid particle at successive instant of time. So we are going to observe only a single fluid particle and it will be able to find out the direction of velocity of that single fluid particle with different times, okay, with different instant of time. In case of steady flow, as we know that always the time is constant, since there are no fluctuations of the velocity, the path line coincides with the streamline. So in case of your steady flow, the path line and streamline are same, because there will not be change with it or respect to that of the velocity. In case of unsteady flow, the streamlines change their position at every instant, okay, and thus the path line may fluctuate between different streamlines during the interval of time. Okay, so this is the difference between the two, path line and streamline. So in case of path line, we are observing the movement of a single fluid particles throughout its period of time. Okay, and we are finding out the what is it, velocity. So here it is depicted with the path line. So the path line will not be like a regular streamline or a straight line. So here it will be like in a zigzag motion. So if you are studying about this okay, the particles behavior at different instant of time, then it is said to be, then you will be able to get the velocity at that instant of time, and that is said to be your path line. Okay, so here what you could see this, this particle, they have the pass through the origin at the time t naught, that is with different times also will be able to see. So here this particle pass through the time at t1, and this particles will be passing through the origin at time t2. Okay, so with different time period, this particle is moving from the origin. Okay, so this could be able to see with the help of a path line. So here we are going to find out what is the path, or what is the line that is actually described by a single fluid particle when it moves during a period of a specific time. Okay, next is streak line. What is streak line is? It is a locus of the position of fluid particles which have passed through a given point in succession. Or it is in a simple term, we can say that it is a line that is traced by a fluid particle passing through a fixed point in a flow field. So in case of path line, what we do is whenever the particle is traveling, we will be going behind that particle, and we will be observing that particles, okay, that and we will get the velocity at the instant of time what is required. But in case of streak line, we are not going along with the particle, instead we are going at a point in the fluid flow. So this is a common fluid flow. So in the fluid flow, at a given point, we are going to find out the position of the particles, okay, which have passed through the point. Okay, you mean succession in the one after the other, how it has been going to pass, that we are going to study. That is called a streak line. Okay, so this is a line that is traced by a fluid particle passing through a fixed point in the flow field. Suppose we have ABCD or the particles which are passing through the reference point. Say the origin is the reference point, one after the other in succession. These particles have described their own path lines. Suppose at time t, these particles are at PA. Okay, then the line PA, PB, PC and PD is called a streak line at the time t. Okay, so this you could be able to see here. See, what I said is the particles are originating from a single point, and it's go on moving here. Okay, so this is known as your path line. Okay, but at a single point in the flow, if you are finding out this properties, okay, so that is said to be your streak line. Okay, so at the single point in the flow, it's not with a variation of your fluid particles. Okay, we are not going with it of the movement or along with the movement of the fluid particle. Instead, we are going to find out what is the behavior of the fluid particle at a single point in the flow field. Okay, so in that case, will the line PA, PB, PC and PD, now this is the line which gives you the streak line. So this is your path line where the different particles will be starting at different time, and it goes on moving like this. Okay, so that will be studying along the particles. But at a particular point, if you are able to find out the particle, and if you are going to draw this, okay, so that line is said to be your streak line. So what is the difference between path line and streamliners? So the path line is, as I already said, it is a path that is followed by a fluid particle over a period of time. But streamliners, it's an imaginary curve in the fluid flow, because we cannot draw the fluid flow curve. So we are drawing an imaginary curve in the flow field for a fixed instant of time. Tangent to give, which gives the instantaneous velocity at that point. Okay, so two path lines, they can intersect each other. Okay, path line can be intersect each other, or single path line can form a loop as different particles, or even same particle can arrive at same point at different instant of times. So in case of path line, what happens is even the single particle can be able to form a loop like this. Okay, and it can be able to travel, or even the same particle can arrive at the same point at different instant of time, because this will be able to cross each other, so intersect each other also. So that could also be possible in case of path lines. But in streamlines, the two streamlines will never intersect each other. Okay, so it will not even intersect each other. That means it follows some straight line, or what you say, it is a parallel things. Okay, which will not get intersect each other. As the instantaneous velocity at any given point is unique. Why? Because it doesn't intersect, because the velocity vector at any given point is unique in case of a streamline. But in case of steady flow, both path lines, they will be identical to the streamlines, and hence the Eulerian and Lagrangian versions becomes the same for both the path lines as well as the streamlines. That means the flow will behave like, the path lines and streamlines will be the same in case of a steady flow. Now next comes your stream tube. What is a stream tube? This is your stream tube. So where we have a imaginary tube, this is not the original tube. We are considering an imaginary tube. So this is a fluid particle that is moving. So we are going to draw a number of imaginary tubes, okay, which is causing over this, which having this all this path line, streamlines, okay, just by making an imaginary tubeless space that is formed by a number of streamlines. Passing through a small closed curve, which may or may not be circular. It need not to be circular also. So here what is that is the surface of the stream tube is made up of different streamlines. You could be able to observe here. It is not a path line. A path line will be intersect each other, but this is a streamline which will not intersect each other. Okay. So the velocity of the fluid particle on the surface of the stream tube is along the streamline over the surface of the stream tube. Okay, this means that no, there is so what we are observing that here in case of stream tube, these particles will not go and hit the walls. Okay, so we are not going to find out the velocity across the walls of the stream tube. Okay, so the velocity at the centroid of the section, it will be representing the average velocity of flow through the stream tube. Okay, in other words, how we could say this is so what are the fluid that is entering the stream, that is equal to the quantity of the fluid that is leaving the stream tube. Okay, so that is the main thing. That means here we are not going to consider the velocity of the fluid particle on the surface of the stream tube. Okay, because the stream tube is what is the imaginary tube now, which is formed by the number of streamlines. So we are considering that at the surface now there is no velocity, or okay, and so we are not able, we are not going to there is no flow at all across the walls of the stream tube. And therefore what is the flow that is entering the stream tube, it will be equal to the quantity of the fluid that is leaving the stream tube. So what are the properties of steam tube? As we know, the steam tube is bounded on all sides by streamline, not only here, in all the sides, okay, out of this, because we are assuming a single portion, but in all the sides will be having only the streamlines, okay. So fluid velocity does not exist across the streamline. No fluid may enter or leave a stream tube except through its end. So, and we know what is one more assumption we make it is that is the no fluid can exit in any other side. Okay, it cannot enter or it cannot leave in any other side. It could enter only through this tube entry, and it could exit only through this outside exist. Okay, so it will not be there. And some other point, the fluid there has no chance of entry or escaping out. So the entire flow in the flow fluid may be imagined to be composed of flows through steam tubes arranged in some arbitrary portions. Suppose you have a channel, or you if you have a stream. In that case, the entire flow will be imagined to be having the number of stream tubes, okay, arranged in some arbitrary positions. And from that we will be able to find out what is the streamlines, okay, and from the streamline we will be able to find out what is the velocity of the fluid particles on the stream tube. Okay, so here we are not considering on the surface of the stream tube, instead we are going to consider only the along the streamline over the surface of the stream tube. Okay, so that velocity alone we are going to consider here. Next one is properties of stream tube. We have already seen this. Then we are going to see about potential line. So what is potential line? On a surface consisting of streamlines, we can draw imagined lines running orthogonally with the streamline. Such lines are called potential lines. See what is streamline is? This is the movement of the fluid. Okay, so this will be moving in a constant line like this. It goes on moving and it will not intersect also. Okay, so it is a continuous one. It goes on moving here. Now what you are going to do this is, if you draw an intersection at right angles to each other, okay, then that intersection that is called as your potential lines. Okay, so this could be depicted here. So on a surface consists of streamlines, we can draw imagined lines, okay, running orthogonally with the streamlines. Such lines are called as potential lines. Velocity of the fluid particle. So what is velocity? You know, it is the rate of change of displacement of the fluid along that direction. Okay, rate of change of the displacement. So here we are considering the velocity of the fluid is v, general velocity, but with respect to the direction, if you take, we consider the three velocities. One is u, v and w along the components x, y and z directions respectively. So these are the velocity components in x, y and z directions respectively. So what will be the velocity? How you will write it? U is as a function of f1 of x comma y comma z comma t. Okay, with respect to time, because velocity is always change in length by time taken. Okay, and v is equal to f2 is, it's a function of x, y, z comma t, and w is, that is a velocity in z direction, is equal to f3 into x comma y comma z comma t. Okay, so these are the velocity components in u, v and w directions. Now, what is the resultant velocity in a fluid flow? So, resultant velocity is equal to v is equal to ui plus vj plus wk. Okay, or we can say that if you draw the vector, we can get that resultant velocity will be, what is it, square root of u square plus v square plus w square. Okay, so that you will be able to find out the resultant velocity. So where u, v, w are the velocity vectors in x, y and z directions respectively. So what is velocity? It is the rate of change of displacement of the fluid along that direction. Okay, so next is acceleration. So what is acceleration? It is not rate of change of displacement. Displacement is not there, but instead here it is the rate of change of velocity. So both the definitions are almost same. Only in case of velocity, it is the rate of change of displacement. In case of acceleration, it is the rate of change of velocity of the fluid along that direction. That's why the unit for acceleration will be given as meter per second square. Why? Because meter per second is always the velocity. So if we are finding out this rate of change of velocity along with that of the direction, okay, at a particular time, then it is given as rate of meter per second square. Okay, so here what is that is a y and a z and a x are the components of acceleration along these three directions respectively. Okay, so what is the acceleration in x direction will be, we are giving the acceleration. What is acceleration? It is change of velocity by time taken. Am I right? So here the change of velocity in the corresponding direction, say suppose if it is u direction, it will be dou u by dou x with respect to direction, and once again it is the rate of change of velocity is dou x by dou t with respect to time. So we know what is that acceleration is rate of change of velocity with respect to the direction. So dou u by dou x into dx by dt. Similarly, we get it for y direction, dou u by dou y into dy by dt. Similarly, for z direction, dou u by dou z plus dz plus by dt. As well as we have the rate of change of velocity with respect to t time in case of x direction. Okay, so here what happens is we know that dx by dt is equal to u. Okay, and dy by dt is equal to v and dz by dt is equal to w. What is that? Well, it is a velocity. What is velocity? Velocity is rate of change of displacement, or we can say distance by time taken in simple words. So u is the velocity. So what is the distance in u direction? It is x. So u is equal to x by t. Okay, that is, since we are considering small particles, we are taking it as dx. So dx by dt. Similarly, v is equal to dy by dt and w is equal to, it is a velocity in y direction. So dz by dt. Okay, similarly, here what you are doing it up, you are just going to substitute this value of dx by dt, that is your u, v and w in this equations, in this previous equation. So what happens here? you will get it here. Instead of dx by dt, we are going to substitute u. So what is the equation will become? U into dou u by dou x. Similarly, v into dou u by dou y plus w into dou u by dou z plus dou u by dou t. So this is the acceleration in x direction. Similarly, acceleration in y direction will be u into dou v by dou x plus, see here what is the difference between these two equation. Here everything in x direction, everything the velocity in terms of u. In y direction the velocity is in terms of v, and z direction the velocity is in the terms of w. All other things are same. Okay, so what is that is velocity components uvw plus time, that will be that. And apart from that, velocity changes with respect to dou u by dou x, dou u by dou y and dou u by dou z, that is your acceleration in x direction. Similarly, in acceleration in y direction will be u into dou v by dou x plus v into dou v by dou y plus w into dou v by dou z plus dou v by dou t. Similarly, we could get the velocity in the z direction. But in the case of steady flow, what is a steady flow? The velocity component with respect to time will be equal to 0, or it will not changes with respect to time. Okay. So here that time equation we are removing it up. So for steady flow, what will be comes when some dou u by dou t is equal to dou v by dou t is equal to dou w by dou t is equal to 0 for steady flow. So in this equation, we are neglecting this, all these values dou u, dou v, dou t and all those things with respect to time, because the steady flow is, it's the behavior of the fluid when the velocity, even if we are studying the velocity parameters or the flow parameters, which will not change with respect to time. Okay, so here it is not changing with respect to time, that means this is equal to 0. So the equation will become, here already we have shown that it has been removed. So ax is equal to u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z. Similarly, we get the value of equation for ay as well as az. So ay is dou v by dou x plus v into dou v by dou y plus w into dou v by dou z. And az is u into dou w by dou x plus v into dou w by dou y plus w into dou w by dou z. So what is the acceleration vector here? Acceleration vector is axi plus az plus azk. That will be your total acceleration vector. So axi is, ax is acceleration with respect to x direction, plus ayj is the acceleration with respect to y direction, and azk is the acceleration that is respect to z direction. So what is the acceleration vector? Root of ax square plus root of ay square plus az square. So all under the single root. So root of ax square plus ay square plus az square. So that is your acceleration vector. Now from this equation, you will be able to find out what is the local acceleration and convective acceleration. So local acceleration is otherwise called as temporal acceleration. Okay, temporal acceleration. And so the total acceleration will be, it is equal to temporal acceleration, means the acceleration with respect to time, plus convective acceleration. So this temporal acceleration is otherwise said to be our local acceleration. So in these equations, in all these three equations, with respect to time now, that is said to be our local acceleration, and with respect to the space, that is said to be our convective acceleration. Okay, similarly in the case of az also. Okay, so in case of az also, this is your local acceleration or temporal acceleration, and this is your called as your convective acceleration. Okay, so but in case of steady flow, what happens is this temporal acceleration will become to 0. Okay, as it will not change with respect to time, the flow parameters will not change respect to time. So this will become 0, only we will be having a convective acceleration. Okay, so next is your velocity potential function. So what is velocity potential function? Means it is a scalar function with of space and time such that its negative derivative with respect to any direction will provide us the velocity of the fluid particle in that direction. Okay, we have a function with respect to space and time, and if you have the negative derivative with respect to any direction, it will be providing the velocity of the fluid particle in that direction. And normally this velocity potential function is represented by the symbol called pi. So you will be able to know this is called as pi. So u is, what is u? It is, the velocity in x direction. Okay. So how the velocity potential function is given as, it's given by the negative derivative with respect to the direction. Okay. So negative derivative with respect to direction is minus dou pi by dou x. Similarly, it will be represented in case of y direction, it is minus dou pi by dou y. And in case of z direction, w is equal to minus dou pi by dou z. From this, you will be able to know it is a scalar function of space and time, whose negative derivative with respect to any direction, x direction, y direction or z direction, will provide us the velocity of the fluid flow in that direction. That is, it provides the velocity u, v and w in the corresponding direction. So velocity components in the cylindrical polar coordinates will be like, suppose this we are given in Cartesian coordinates. If it is a cylindrical polar coordinates, it will be given in terms of thetas. Okay, so it will be dou pi by dou r is equal to ur, and 1 by r of dou pi by dou theta is equal to u naught. Okay, where ur is a velocity component in radial direction and u theta is a velocity component in the tangential direction. Okay, so this is in the case of your polar coordinates. Now we know the continuity equation. Already we have seen what is the continuity equation for an incompressible steady flow. That is dou u by, for 3-dimensional, it is dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0. So in this equation you have here u, v, w. Okay, instead of that u, v, w, you substitute this values. Okay, that is u is equal to minus dou pi by dou x, v is equal to minus dou pi by dou y, and w is equal to minus dou pi by dou z. That is your velocity component potential function. So here in this continuity equation, we are substituting the value of u as minus dou pi by dou x and v as minus dou pi by dou y and w as minus dou pi by dou z. In this continuity equation, we are substituting the value of u, v and w. So what does the equation becomes? It is dou into dou is dou square. Okay, here we have dou, here we have dou. So dou into dou is dou square. And dou x into dou x is dou x square. So how the equation will become? Dou square pi by dou x square. Since negative is on all the three directions, we are removing the negative term. So the final equation will be dou square pi by dou x square plus dou square pi by dou y square plus dou square pi by dou z square is equal to 0. And this equation is said to be the Laplace equation. Okay. Now here, for 2-dimensional case, how this Laplace equation will be that 2-dimension means we don't have one direction. Okay, one dimension is not there. So this is a direction, we are removing it up. So what your Laplace equation will be? Dou square pi by dou x square plus dou square pi by dou y square is equal to 0. This is the case of 2-dimensional flow. Okay, so this is the Laplace equation. Next one is your properties of the potential function. What are the properties? So the rotational components, now if it is a rotational flow, if it is rotational components will be given by this equation, that is wz is equal to half of dou v by dou x minus dou u by dou y. Similarly, rotational component of y direction and z direction is also given here. So when you observe this equation, you will be able to find out that see here you have z, and this z is not being replaced here. Once again we have the other two directions x and y. Suppose if the direction is y, then we have the directions here is only z and x, not the y inside once again. Okay, so this you will be able to recall easily when you write this equation. So the rotational components of wz is given, that is half of dou v by dou x minus dou u by dou y. Okay, it is not with respect to the same velocity. Okay, it takes the velocity of here or a different velocity in the different direction. Okay, so this is your rotational component. Why? Because it rotates with not respect to the same direction. It rotates, so therefore the velocity will be changing with different to the different direction. So now here also what happens, you know this equation, substituting the value of u, v, w. Okay, what is your equation? Here you have half of dou v by dou x minus dou u by dou y. Okay, so just consider this equation. So in this equation you substitute the value of v and u. You know the value of v and u. What is that? Dou pi by dou y and dou pi by dou x. So you substitute the value here and you solve it. You will get the final equation as half of minus dou square pi by dou x dou y plus dou square pi by dou y dou x. Similarly in y direction and similarly in z directions we get this values. So what is the if it is pi is a continuous function, then what happens is dou square pi by dou x dou y plus dou square pi, that is equal to dou square pi by dou y dou x, and dou square pi by dou x dz is equal to dou square pi by dx dz. So it is a continuous, means dx dy will be equal to dy dx and dz dx is equal to dx dz. Okay, so that's it can be happen in case of a continuous function. So and we are considering that waz, wy, wx is equal to 0. When rotational components are 0, the flow is called as irrotational. So here we consider only the rotational components. If the rotational components are 0, then the flow is called as irrotational. Hence the properties of the potential function is that if the velocity potential exists, the flow should be irrotational only. If the velocity potential pi exists. If the velocity potential satisfies the Laplace equation, it represents the possible steady, incompressible, irrotational flow. Okay, so these are the different properties of the potential function. Next one is your stream function. What is a stream function? It is a scalar function of space and time such that its partial derivative with respect to any direction gives the velocity component at right angles to that direction. So here we are giving the partial derivative with respect to any direction will give the velocity component at right angles to the direction. And this is also a scalar function of space and time. So here the stream function is given by the symbol psi. So in the earlier case we have seen the velocity potential function which was denoted by the symbol pi, and here the stream function is going to give the psi. Okay, so now in case of two-dimensional flows, what is the psi? Psi is a function of x comma y. Okay, now what you are going to do is differentiate with psi with respect to x. Okay, that is dou psi by dou x will give you the velocity at that corresponding it will not give the corresponding direction, it will be giving at right angles to that direction. See here we have x direction, so what is the velocity right angles to that direction is v. Suppose if it is y direction, what is the velocity right angles? It is minus u. So dou psi by dou x is equal to v and dou psi by dou y is equal to minus u. So in case of your potential function, if you remember that in case of your potential function, here also this scalar function of this, where it will be giving the negative derivative with respect to any direction, will provide the velocity. So here we get u is equal to minus dou pi by dou x and v is equal to minus dou pi by dou y and w is equal to minus dou psi by dou z. It will be giving the what is it corresponding direction itself. If you observe that equation, you will be able to know if it is u, the corresponding x, if it is v, the corresponding y, if it is w, it is corresponding z. In the corresponding direction itself it gives. But in case of a stream function, it is not giving the corresponding direction, it is going to give at the right angles to that direction. Okay, so here what is the right angle for x? Right angle is y direction. So what is the velocity in y direction? Y right angle is x direction, so it is given in terms of minus u. So dou psi by dou x is equal to v and dou psi by dou y is equal to minus u. How do you pronounce this word as psi? So it is psi. How do you pronounce it? Psi. Okay, so this is your mathematical fast steady flow equation. So what is the properties of stream function? As we already know, what is the continuity equation in two-dimensional flow? That is dou u by dou x plus dou v by dou y is equal to 0. Okay, now in this equation, what is the unknown for value for you? You know what is u and v, substitute here. So you are substituting the u and v in terms of psi. So in the previous case, you have substituted in terms of pi. Now we are going to substitute in the terms of psi, that is your stream function. So what is your equation will become? Minus dou square psi by dou x dou y plus dou square psi by dou x dou y equal to 0. Okay, so what happens here? As it satisfies the continuity equation, the existence of stream function proves a possible case of fluid flow. This flow can be either rotational or irrotational. If the rotational component is given, we know the rotational component, what is it? Wz is equal to half of dou v by dou x minus dou u by dou y. Similarly, we have it in the other directions also. Okay, so in this equation, you substitute what is the value of v as well as u in terms of psi. Okay, that is why we have substituted here. It is in v in terms of psi is dou psi by dou x and v u in terms of psi is dou psi by dou y. Okay, just you substitute this and here with the negative terms. Okay, so what is your final equation of w is at half of dou square psi by dou x square plus dou square psi by dou y square. For irrotational flow, w will be equal to 0. That is, rotation will be equal to 0 because this is a rotational component. W is a rotational component we have taken. So what is this equation will become? So this equation will be equal to 0. So half will also we can get removed. So it is dou square psi by dou x square plus dou psi by dou square psi by, sorry, this is given wrong, dou square psi by dou y square is equal to 0. Okay, which is the Laplace equation for psi. So we have found out what is the Laplace equation for pi and what is the Laplace equation for the psi. So what are the main properties of stream function is the existence of stream functions. It proves a possible case of fluid flow that can either be rotational or irrotational in nature. A stream function of a fluid satisfying the Laplace equation is supposed to have an irrotational flow. So suppose if the stream function satisfies the Laplace equation, then such flow should be a irrotational flow only. Okay, now we are going to see the line of equation of stream function. We know what is that stream function and we have given this dou psi is equal to dou psi by dou x of dx plus dou psi by dou y of dy is equal to 0. Okay, we know dou psi by dou x is what is it. So this is the line of equation of stream function. That is stream function with respect to x direction and stream function with respect to y now. That is equal to 0. So where this dou psi by dou x now, that is equal to v, and dou psi by dou y, that is equal to minus u. So substitute in this equation number 1 this values. What happens here? V dx plus, sorry, here minus is there, so minus u dy is equal to 0. Am I right? U dy is equal to 0. So which is represented here. So v dx minus u dy is equal to 0. So just if you rearrange it and if you are bringing it up, it will become dy by dx is equal to v by u. And this dy by dx will be giving you the slope of the streamline. So if you want to know the slope of the streamline, you will be able to find out by using this. Okay, dy by dx is equal to v by u. By using this, we will be able to find out the slope of the streamline. So what is the relation that connects between the stream function and the velocity potential function? We have already derived what is the velocity in terms of stream function and velocity in terms of potential function, velocity potential function. So here those two equations are given. So velocity u in terms of, that is your x direction, no, that will be that way the velocity in terms of velocity potential function, it is minus dou pi by dou x, and v is minus dou pi by dou y. So this is said to be your pi, and in case of your stream function, it is dou psi by dou x and dou psi by dou y. Okay, so dou psi by dou x is equal to v, dou psi by dou y equal to minus u. Now you just observe these two equations. You will be able to find out a connection between these two. Okay, just we will see here. What is that is? Now you take the case of u. What is u here? Minus dou psi by dou x. What is u here? It is also minus dou psi by dou y. It is in terms of stream function, that is in terms of velocity potential function. So what you observe from this? From this we observe that dou psi by dou y is equal to dou pi by dou x. Am I right? And similarly in case of v, if you are finding out that is your velocity in z direction, y direction. So in this case, what is that? Your potential function minus dou pi by dou y. So here in case of stream function, velocity is dou psi by dou x. So what is the difference here? Only thing is we have to equate this v and that v. So what will be that? So dou pi by dou y is equal to minus of dou psi by dou x. So this could be given here at this. So what is this? This is the relation that is connecting. That is, if we know the velocity potential function, we will be able to find out the stream function. Or if we know the stream function, we will be able to find out the velocity potential function by these two equations. Okay. So by comparing these two equations, just now we have did it. So what is it? Dou pi by dou x is equal to dou psi by dou y. And dou psi by dou y is equal to minus dou psi by dou x. Okay, so this is your terms of pi and this is in terms of psi. That is, your pi is your velocity potential function and psi is a streamline function or stream function. So what is the difference between the stream function and velocity potential function? See, stream function will be applicable only for 2D flows, but velocity potential will be existing for all flows. And stream function will exist for either viscous or non-viscous flows. But velocity potential will be existing only for irrotational flow or where there is a zero viscosity. And the stream function, it exists for incompressible flow, both steady and unsteady state. Similarly, velocity potential function is also given for incompressible flow, both unsteady and steady state. And stream function will be given for compressible flow, steady state only. Okay, but this velocity function will be given in terms of compressible flow, both steady or unsteady state. So this is the difference between your stream function as well as a velocity potential function. Now we will go for the next thing, that is your equipotential line. Now, what do you mean by equipotential line? So the line along with the velocity potential pi is constant. Okay, if the velocity potential pi is constant, then that line is said to be a equipotential line. Or we can say in other terms that dou pi is equal to 0. If we differentiate with respect to pi, it will be equal to 0. So what is your equation? Dou pi is equal to dou pi dou x of dx plus dou pi dou y of dy. And we know dou pi by dou x is, what is it? Dou pi by dou x is, it is u dx, and dou pi by dou y is v. Okay, so it is both are in negative integration. Do you remember the velocity potential function? It both are has to be in the negative derivative. Okay, so here we are giving us a negative minus of u dx plus v dy. We are just substituting the value of pi by x is minus u and dou pi by dou y is minus v, and we are bringing the minus con outside. So it will be minus of u dx. Okay, u is the value of dou pi by dou x. Plus, since we are taking the minus common outside, here we will be getting v dy. Okay, so for equipotential line, what is that is, this dou pi will be equal to 0. That is what our concept. Okay, so that is a line along which the potential, velocity potential is constant. So now we are going to equate this dou pi is equal to 0. So what happens is, this equation u dx plus v dy, that is equal to 0. So here you got that equation, minus of u dx plus v dy. Need not bother about the minus sign. We are removing it up. We are equal to 0 it up. So what is happening? U dx plus v dy equal to 0. Now you rearrange this. You will be able to find out dy by dx is equal to minus u by v. Remember, in case of that equipotential line, we were getting that dy by dx is minus u by v, and this dy by dx will be giving the slope of equipotential line. Okay, so in the previous case of your streamline, okay, where the slope of the streamline is given by v by u, it is not u by v, it is v by u, and this is the equation that is giving the slope of the streamline, that is dy by dx is equal to v by u. Okay, that is in positive. But in case of your equipotential line, here dy by dx is equal to, it is not the corresponding direction of your, what is that, velocity, it is opposite direction. So if you have here dy, it is u, and here dx, it is v. So okay, it is minus. Okay, it is that term. So this is the slope of the equipotential line. So you will be able to find out the slope of the equipotential line if you know the velocity u and v. Next is your flow net. See, what is a flow net is, what is a net? What is a net? It is just like a, how do you say the net? Net will be like, it will be like a mesh. Am I right? It will be like a mesh. The same way, when this mesh will be created, when we have a potential line or equipotential line, when it crosses the streamlines, okay, so then this flow nets will be formed. So this flow nets will be like square shapes, okay, and if you connect out all these diagonals, now once again, if the square shapes has been formed, then we know that this flow net is correct. Okay, so here the flow net is very useful in analyzing the two-dimensional irrotational flow problems, and this flow net is usually like a square mesh. Okay, however, in the regions where the boundaries converge or diverge or bend, the flow does not contain squares. See, suppose if the boundary, if I am having a boundary, if I am having a pipe which is having a diverging cross-sectional area, so it's most like diverging is it is having like this. So what happens here? The flow will be flowing here, But at this point where it's get diverged, in this case the flow will be getting split up. Okay, it will not follow the same thing. Okay, so in this case it is very difficult to get the flow net for these conditions. Okay, so it will not be like square in shape. Okay, so that is where the boundaries are converge or diverge or bend. The flow net does not contain a squares. Okay, and the flow net can be constructed only in the following situations: when the flow is steady, that is we are assuming that the it will not change with respect to time. Okay, and that is that. So in the case of steady condition, we will be able to construct this flow net. And the flow should be irrotational. If it rotates, we will not be able to find it out. So what we assume that it is a possibly an ideal fluid that is having no viscosity, or it has a negligible viscosity. And the flow net should not govern by the force of gravity, because under the action of gravity the shape of the free surface changes constantly and we cannot get a flow net pattern also. Okay, so under this conditions we have to consider the flow net. So this is a flow net, as I already said here. What happens is you have a streamline. Okay, so this is your streamline. When you draw the equipotential line, okay, equipotential line is always orthogonal to that of the streamline. We draw it up. Okay, and this will form. Okay, and we consider this at each area. We will be considering that as a, what is it, a steam tube. No issues. Okay, we can consider that as a steam tube. Yeah, at any flow we can consider at any point that is a steam tube. Now what is it? This square one like a mesh type, so that is said to be a flow net. So this could be constructed in case of a steady flow, irrotational flow, as well as where the force is not governed by the force of gravity. Why do we want to study this flow net? So there are before seeing that, we'll see what are the different methods of drawing the flow net. So what we can do it is by analytical method we can do it. What is that is we can get an equation for a stream function. We can get an equation for equipotential line as well as streamline, and by solving this we will be able to find out the flow net. But what is the difficult task in this is the solving this equation in case of irregular boundaries. Okay, that is not possible with the help of your analytical method. That's why we go for the graphical method. So in case of graphical method, even if it is any irregular shape, we will be able to draw the flow net. But we consider this okay, boundary as a fixed one. Okay, and we will be able to draw this flow nets with respect to this boundaries in graphs, and we will be able to get the value of flow net. Okay, and other one is electrical analogy method, in which what we assume that is electrical current, or that will be it will be analogy to that of our velocity. Okay, so that both will be get in analogy. So that is the main assumption what is made in the electrical analogy method. And other one is we have relaxation method and Elisha viscous flow analogy method. But normally we go with the graphical method. Okay, if we are not going to determine by experimental way or practical way, if we want to do it with a practical way, then electrical analogy method is a practical means of drawing the flow net. So what are the applications of flow net? So why we want to find out this flow net? So this will be helpful to find out the behavior of the irrotational flow. Okay, so this will help to depict as well as analyze the behavior of the irrotational flow. And many flow phenomena, it cannot be analyzed only by mathematical means. Okay, that can be analyzed by drawing flow nets. So which could not be analyzed by mathematical means. So such flow phenomena we can analyze by using drawing the flow nets with the help of a graph. And it also assists in the determination of the boundary shapes for which the flow does not separate from the boundary surface. Okay, we are assuming the boundary shape that we can be done, and we are assuming that the flow is not going to separate at this boundary. Okay, it is not going to separate. So it will be helpful to find out the determination of the boundary shapes. And very importantly, through divergent boundaries, this flow net is not possible. As I already said, it is not possible through the divergent boundaries. But however, it can be possible with the convergent boundaries, where the diameter gets converged or it is get reduced. So what happens here, it will not change much in this path. Okay, it will moving in the same way. So the flow net drawing will be is also easy here when we draw the equipotential line. But in this case, when it is divergent, if you draw the equipotential line, it will not be like what is a diamond shape. Okay, it will not be like a diamond shape, because the fluid will be moving like in a divergent pathway. Okay, so this will not holds good in case of a divergent boundaries or divergent pipes. And these are the further some of the important uses of flow net analysis. For given boundaries of flow, the velocity and the pressure distribution can be determined. If the velocity and pressure distribution at any reference section is known, we will be able to find out the velocity and pressure distribution at the given boundaries of the flow. And the loss of flow due to seepage in earth dams and unlined canals, that can be evaluated by using the flow net. Okay, how much is the flow loss because of the seepage? What is the seepage? This is once again a leakage. Okay, leakage in the dams or canals, unlined canals. So that loss of flow can be easily evaluated by use of this flow net. And uplift pressures on the underside of the bottom of the dam can be worked out. Okay, what is the uplift pressure because of the water at the bottom of the dam? That can be easily worked out. And outlets can be designed for the streamlining. So that could also be possible with the help of your flow net. But we have some limitations of this flow net also. That is, it cannot be applied in the region close to the boundary where the effects of viscosity are predominant. So, if the viscosity are predominant in the boundaries, then we cannot go for doing this flow net. But normally, why we say that we consider that this boundaries will not be affected with much with that of the viscosity. So that only the flow net will be able to do it up. And we cannot do it very specifically for the sharply diverging flow, as I already told you. Okay, so it cannot be done for the sharply diverging flow. And similarly, suppose if this fluid passes a solid body, okay, in that case also we will not get a correct information at the rear of this fluid because of the separation and eddies. Okay, so suppose you have a solid particle and if the fluid passes like this solid particles, what happens here? We will not be able to get because of the eddies now. So when it hits here, some forces will be get and you will be getting some eddies. Okay, so what happens is because of this eddies we cannot find out what is the flow condition at the rear. Okay, so because of this separation, and it will also get separated like this. So because of the separation as well as because of this eddies, will not be able to get out what is the exact flow condition at the rear. So the disturbed flow in the rear of the solid body now, that is known as wake. Okay, and the formation of which is not indicated by a flow net. So in the flow net we will not be able to indicate this wake, or that is what is a disturbed flow when we have a solid body and when the fluid is passing through this. So what is a disturbed flow because of the separation and eddies now, that is said to be a wake, and that cannot be easily indicated by a flow net. Okay, so these are the things with respect to the kinematics of flow. So today what are the things we have seen? We have seen the different streamline, streak line, path line, stream function, velocity potential function, as well as flow net, and what are the how to measure the flow nets and what are the advantages and limitations of flow net. Okay, so for this things you can refer the Fluid Mechanics by R.K. Bansal and Fluid Mechanics by Modi and Seth. So these are the two books you can go for referring it up. Okay guys, thank you. We will see in the next video.